Statistics is really thinking about how we can present and how we can study a set of chance outcomes. That's our data set. So these chance outcomes might come in the form of numerical data, so something that we can count or measure in some kind of numerical way, or they might come in a categorical way. So we could think about like the color shirts everyone in the class is wearing. You get put into the red shirt category, the blue shirt category, the green shirt category, etc. So whenever we have a process that generates this data for us, we call it an experiment. And you'll notice experiment here is used a little bit more loosely than it is in science. Experiment has a much broader range of options. So we might actually have something that has the controls that a scientific experiment has, but we also might have something as simple as looking at the color shirts of the students in the classroom. So we use the word experiment in a variety of ways. So bear with me with that word being tossed around a little bit more loosely than you're used to. So now we're going to jump into the vocabulary and some examples of what that vocabulary really means that we'll be using when we're talking about basic probability. Whenever we talk about the sample space when we're dealing with probability, we're talking about the set of all possible outcomes of a statistical experiment. So, an example of that, the sample space for flipping a coin is the set of outcomes, heads and tails. So this is the sample space for a coin flip. And if we rolled a dice, a six-sided die, we could have a 1, a 2, a 3, a 4, a 5, or a 6 as our outcome. So that's our sample space. For a single die. Another word that we toss around a lot is an element. Sometimes we call it a sample point. All right, so what this is this is every single entry in a sample space. So each entry in a sample space is an element of that sample space. Also, sometimes I say sample point, we also sometimes call it a member. So we've got lots of words we can talk around. I'll try and keep it to element. Every once in a while I'll probably slip to member. I'll rarely call it a sample point. When we're thinking about what sample spaces are, and we're doing multiple things along the way, sometimes it can get complicated to figure out what the elements in that sample space should be. So one of the tools that we have at our disposal to help us out with that is a tree diagram. So to make a tree diagram, what we do is we think about what we're going to do first and then what we're going to do second, and we build it up. So in this example, the first thing I'm going to do is flip a coin. So this is my first part of my experiment. So outcome 1 is what it'll be. So when I do this, I'm going to flip a coin. What are the possible outcomes of flipping a coin? You got it. It's heads, or it's going to be tails. It's got to be one of those two. So then If I go for my second option, we're going to flip it again if it's heads. So if out of my heads outcome, I'm going to flip a coin again, so I'm going to get heads or I'm going to get tails. And if it's tails, I'm going to roll a die instead. So for tails, I'm going to have outcomes coming out of it that are 1, 2, 3, 4, 5, and 6. So this is going to be outcome 2. This is the second part of my experiment. So when I'm looking at and what I'm really trying to get out of all of this, right, is actually my sample space. So my sample space let's say here's the element, right? So element, there we go. So each one of these results in a sample space element, and we figure out what it is by coming along our tree and reading from left to right. So I've got heads, heads. So this sample space element is heads, heads. The next one, I'm going to read across. I get heads, tails. And then I'll get tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. And when I put all of those elements together, this right here is my sample space. And I should write my sample space with curly brackets, and I list out all the elements with commas in between them. So heads, 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 tails, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. And that's the sample space that I get from running this experiment. Sometimes it's not realistic to be able to list out all of the elements in the sample space. So your book gives an example of cities with over 1 million people in it in the world. It's just not at all a realistic thing to write out. So if I'm trying to write a sample space like that, I can use the curly brackets still, but what I do is I use this method of writing it that gives me a statement that has to be true. So the sample space here is going to be all of the x. X is just a placeholder variable here, such that x is a city with a population over 1 million. And we close out the curly braces. So what this is saying is it's going to be all of the x such that x is a city with a population over 1 million. So this is going to be all the cities with a population over 1 million. So what this has for us is it has this placeholder variable, and then with it, it has what we call a rule. So all of this right here, it's my rule. Right? And that tells me what has to be true about my variable in order for it to be included in my sample space. Now, whenever we talk about an event in statistics and probability, we're talking about a subset of a sample space. So we might have the event that a coin flip is heads. That's heads was a subset of our sample space. Events can consist of one or more of the outcomes. So I might have the event that a coin flip results in heads or tails. So really in that case, it's the entire sample space. Or I might have the result that, or the event that a coin flip results in neither heads nor tails, and it's really called the null set or the empty set, and we write it as this. So it's none of the elements in the sample space. Another word that gets tossed around a decent amount is the complement of an event. So what we're talking about here is everything in the sample space that is not part of the event. So say I have my event is the die roll. Nope, die roll, should spell that right, yeah. Die roll is even. So my event is going to be that the die roll comes out 2, 4, or 6. And I'll call that event A. All right. So when I talk about the complement of event A, so the complement of A, which we write A with a little apostrophe after it, all right, is all of the elements in my sample space that are not in my event. So my sample space, remember, had the numbers 1 through 6, so my complement of A is 1, 3, and 5, because those are the 3 numbers in my sample space that are not in my event, not part of the event. Whenever I'm talking about more than one event, I can talk about the intersection of those events. So if 2 events have nothing in common, then the intersection of them, you think about the intersection of 2 roads, if they never intersect each other, they have nothing in common, then there's nothing there. If I think about 2 roads that do intersect, then there's some pavement that they share. So when we think about this intersection, say I have event A is the same as my event before. So I'm rolling a die and I get a 2, 4, or a 6. And say I have event B, I'm rolling a die and I get 1, 2, 3, or 4. So now, if I want to know what the intersection of those 2 events is, so I write A with this thing like an upside down U, which also kind of looks like an A without a crossbeam in it with you rounded off. This is the symbol for intersection, or intersect, as we'll say it. So A intersect B is going to be all of the elements of the event that are shared between both events. So I have a 2 in both A and B, so 2 gets in here, and I have a 4 in both A and B. So any element that's in A and B, that's why I like to think about this upside down U as an A, because it stands for and. It ends up in the intersection of the 2 events. Now notice that when we were talking about the complement, A and its complement are always going to have an intersection. So A intersect A prime is always the empty set. In fact, we say that 2 events are mutually exclusive. We use that word when they can't happen at the same time, so they don't share any elements at all. So when I have some event A, say it's my 1, 2, 3 event, and I've got an event B, which is the event that a 6 is rolled. I say that I look at A intersect B, and that's going to equal the empty set. So I say A and B are mutually exclusive. So again, the key thing I'm looking for to find mutually exclusive is that intersection is going to equal the empty set. Another word that I toss around for mutually exclusive sometimes is disjoint. So the idea that they have nothing in common, they're disjoint from one another. Going a slightly different direction, thinking about what two events have in common and thinking about wanting them to be completely separate to be disjoint or mutually exclusive, I can take the union of two events. So the union of events I represent with a thing that looks like a U for union. Right. So this thing's right here, union. That's our symbol. All right, so A union B, let's look at an example. Just makes it the clearest. So say I have A equals my 1, 2, 3 event, and B equals my event of rolling a 6. Then A union B is going to be everything that's in A or in B. And so I put everything that's in A and everything that's in B. So if it falls into one of them, it falls into their union. You put them all together. Bring things together, unite them, all right? When we're talking about mutually exclusive events and we're talking about unions, it can get kind of sloppy and messy and trying to figure out what's going on and what's in what. So we, again, have a visual tool available to us called a Venn diagram. So you've probably used these, maybe not in a math class, but probably in like an English class when you're trying to get stuff together for a essay or something like that to figure out what they have in common. So what we end up doing is we can draw circles that intersect each other. So the most that we'll ever really see is going to be 3, and they tend to intersect each other in that way. So let's take a look at an example with this. So I'm going to have event A be represented by being the event that I roll a 1, 2, or 3 on the die. I'm going to have event B be the event that I roll a 3, 4, or 5 on the die. And I'm going to have event C be the event that I roll a 1, 3, or 5. All right, so what I do with my Venn diagram is I label each circle. So what I'm going to do is I'm going to represent event A with purple. So here's event A, it's this circle right here. So here's event A, it's this circle right here. I'm going to represent event B with red. So this is event B, it's this circle. And event C is going to be blue, and it is this circle. So if you notice, I have places where my circles are overlapping. So when I go to fill in the elements that are in these events, I need to look and see what overlaps. So notice this region right here is actually in all 3 circles. So whenever you're filling in a Venn diagram, I highly recommend that you start in that region, that center region that's in all 3 circles. And you look for any elements that are in all 3 events. So in this case, actually, the number 3 is the only one that's in all 3 events. So I fill a 3 into that region. And now you don't have to do this. I like to kind of keep track of that I've put an element in so that I don't forget an element in an event along the way. So then I go back to my Venn diagram and I notice that I have these regions. There are 3 of them that are shared by pairs of circles. So looking at that, this region right here is shared by A and B, but it's outside of C. So I'm going to look and see if there are any elements that are in A and B, but not in C. And I don't have any of those. So there's nothing in that region. So I leave it completely blank. All right. And then I can look at what's in A and C for this region right here that is not in B, because this region falls in A and B, but not in C. So A and C, sorry, but not in B. A and C share a 1 in common, so I'll put the number 1 in that region right there, and I'll mark it off as an element that's been taken care of. And then finally, I'll come over to my third of these 3 regions, and I'll look and see that it overlaps with C and B, but it's outside of A. So C and B both have a 5. And I've taken care of that element, so I'll mark it off. Now I go to my outer regions. So I have this circle here that's A, but it is none of the rest of the circles. All right, so A, does it have any elements that are left in A that are not in the others? And it does. It has a 2. So I'll put a 2 there, and I'll mark it as taken care of. All right, and then I'll go to my B area that's in B, but not in any of the others. And I'll look for anything that falls in that region. Does B have anything that's not taken care of? It does. It has a 4. So the 4 will go in that region. And then I'll finally come over to C, and I'll look, and I'll say, is there anything that's in C that's not in A or B? And the answer is no, so I'll leave that one empty. And now finally, the last thing you need to look at is think about the sample space of rolling a die. So I should have had a 1, 2, 3, 4, 5, and 6 all taken care of. So if I go through and I look and see what did I take care of, I took care of 1, 2, 3, 4, and 5, but 6 is left out. So in a Venn diagram, the last part is it usually falls in a rectangle, and that rectangle represents the sample space. So anything that's in the sample space but not included in any of the events gets represented by being put into the rectangle outside of the circles of the Venn diagram. So that's how a Venn diagram works. The more you practice with them, the easier they'll become, and Venn diagrams can be your best friend through this stuff.